welcome to this week's Keeping Current seminar. And today we'll keep current with respect to team formation. So the idea of ice formation is you start with a crystal and you let it form. The idea of a team formation is you start with Christian Addington and he tells you how they're formed. So take it away, Christian.
All right, good morning, everyone. I hope everyone's having a good day so far. Like Dr. Finkel said, I'm going to be working with anchored team formation games, and this is a joint work with Dr. Judy Goldsmith and Jacob Schleuder. So I'd like to start with a scenario. Imagine you're in charge of separating a bunch of people at a tabletop role-playing game conference, so something like Dungeons and Dragons. You want to separate all these people into different groups that focus on everyone enjoying the game to the maximum possibility. So you want everyone to be happy, you want everyone to love the group that they're in, and you don't want anyone secretly wanting to change groups. So if you do a poor job, you're going to come up with some pretty shocking groups. You know, groups might be yelling at each other, groups might be crying, you might have, you know, Gordon Ramsay come in and tell you that you're not cooking your steak long enough. Things like that could happen. So the purpose of our research is to sort people into these groups where they want to stay in their groups, they love who they're with, and they have a good time. You want to have one of these fun-looking groups where everyone's working together, everyone's laughing, everyone's having a good time. So a little introduction into hedonic games for those of you who may not have researched into them very much. So hedonic games are a subset of coalition formation games, and they focus entirely on an agent's preferences within their own coalition. The word hedonic comes from the word hedonism, where someone only cares about their own values. A coalition is a group of people that strictly belong to that group. So we call the people within these groups or coalitions agents within a hedonic game. And a given set of agents with defined preferences for other agents is called an instance. And then finally, we have a partition, which is a set of coalitions, is stable when all agents prefer their current coalition to all other coalitions. Now, this isn't a strict definition. This is more of a layman's definition. We'll get a little more into it a little bit later. Forming stable partitions is hard for many hedonic games, and this is why we study them. We want to sort agents into coalitions that they like. We don't want people to be forced to be in groups that they don't like. So a little bit more about hedonic games. Like I said earlier, they are characterized solely based on an agent's valuation of other members. So agents value other agents, they value sizes of coalitions, and sometimes they value the inclusion or exclusion of certain members from their coalition. And agents might not always have a valuation of other agents. So if you just met somebody, you might not value them yet. So preferences, different agents in different games care about different things. So for the activity selection hedonic games, agents value coalition size. They don't want to be doing an activity with too many people, but they also don't want to be doing that activity alone. Other games focus on who is included or excluded from a game. These are friend and enemy-oriented hedonic games. So if you have a really good friend, that can outweigh all the other agents that you may not like that much. Or if you have someone that you really don't like, that can outweigh having a couple of friends within your group. And then some further hedonic games value specific pairs of agents. So you really want Gordon Ramsay and an unexperienced chef in your group because he would be yelling at them the whole time and it would kind of throw off the whole group dynamic. But you may want Penn and Teller in your group because they're amazing magicians. They've been working together for 30, 40 years. They're really funny. And despite Teller not vocalizing, him being able to communicate through body language would be very interesting. So our specific hedonic game is called an anchor team formation game, and we focus on Nash stability. Nash stability is based on the Nash equilibrium principle from game theory. So for a coalition to be Nash stable, we want each member of each coalition to prefer their current coalition to any other coalition. And we want that agent to prefer being a member of their current coalition rather than defecting to form a singleton coalition on their own. And within ATFGs, agents will assign numerical valuations to 3 criteria. They will value other members within a coalition, they will value certain pairs of agents, and they will value the game manager for their specific coalition. So some potential famous members that you could have in your coalition. You could have Morgan Freeman. Everyone loves Morgan Freeman. He has an amazing voice. He's an amazing actor. So you would really want him in your group. So you might give him a score of plus 14 out of 20. LeBron James would be another amazing member to have. He always wants to win. He works hard. He doesn't take shortcuts. So having LeBron James might be a plus 17 of your valuation. Some people you might not want may be Kim Kardashian West. She's an actress, but she has a more self-centered career, and you may not like that. You may want more of a team player. So we could give her, say, a -8 out of -20. And then another person you might not want would be actor Shia LaBeouf. He has a reputation of being difficult to work with and not really caring about what other people think. So we might give him a -16 because he could really drag the group back. Continuing, we researched heuristic algorithms to find Nash stable partitions within ATFGs. To do this, we generated instances of size 10, 12, 15, and 25 agents. When generating these different instances, we allowed for a couple things. We allowed for agents to like and dislike other agents. We allowed for asymmetrical valuation between agents. So just because I want LeBron James in my coalition doesn't mean that LeBron James wants me in his coalition. We also allowed for pair valuations. So you might want Penn and Teller in your group if you really like magic and comedy, but if you don't, then you might not want them. And finally, we allowed for self-valuation as GMs. So agents get to decide if they want to be a GM or not. So some famous GMs that you might want to have in your coalition, you might want Martin Luther King Jr. He was a great leader. He was really good at bringing people together and a great speaker. You may want JFK for some similar reasons, very charismatic, very good speaker, good leader. Or you might want Jacinda Ardern, the Prime Minister of New Zealand. She's very popular, she's very charismatic, and a lot of people really like being around her. On the flip side, someone like Napoleon Bonaparte, you might not want to be your general manager, especially if he's, being a little grumpy like he is in this picture. He might take out some of his frustrations on you. You might have to fight against Prussia. I mean, it probably wouldn't be a good time to be with Napoleon. Another person would be Simon Cowell. Simon Cowell can be very critical, and he is very vocal about his critiques. So if you don't want a lot of criticism, he might not be someone you really want leading you. So for our heuristics for solving for Nash stability, we came up with 3. We came up with a selfish round robin approach, a utilitarian round robin, and a variation of local search. So for the selfish round robin, we begin by selecting GMs. And the way we do this is we take all agents that value themselves as a GM and we put them in a list. Then we randomly selected from that list so that there was randomness within the algorithm. Once we randomly selected our GMs, each GM in a set order will pick their highest valued agent. So they will sum up their valuation and all of the members within their coalition's valuation of every potential agent to add. And then the agent that has the highest value, they add to their group. So these GMs keep picking in a set order until all agents have been picked. So you can kind of think about this like the NBA draft. So say you have the first pick, you probably want to pick someone really good, someone that your team values very highly. So you might pick Karl Anthony Towns or Anthony Davis or even John Wall. So in this example, the agents don't have much say in where they go. It's more up to the coalition or NBA team on who they select. For the utilitarian round robin, GMs are selected in the same way. So agents that value themselves as GMs are randomly selected to be in charge. Next, these GMs will select an agent, and their valuation and their coalition's valuation of that agent will be added to the potential agent's valuation of the coalition. And these two values are summed together to create a bid. And so each coalition, each round, will have a bid on a certain agent. So once all the bids have been created, we check to see if any bids are competing for the same player. And then we do a series of tiebreakers. So if one bid is higher than the other, that bid is automatically selected and the other bid is invalidated. So we go through round by round, invalidating bids and accepting bids. And then once every agent has been placed into a coalition, then the heuristic is complete. So this is sort of akin to job offers. So say you are applying at Google to be an AI engineer. And so you interview with the AI engineering team, and you really like this position at Google. It pays well, it has good benefits, and you get to work at Google. So maybe you give Google a plus 15 valuation. You really want to work at Google. It's almost like it's your dream job. Now, the Google AI team likes you. You are a good student. You have maybe a master's or PhD in artificial intelligence, and you have a pretty good resume. But you're not their first pick. So they may give you a valuation of plus 10. So Google currently would add 25 value to their engineering team by hiring you. Next, you might somehow get an interview at the one Blockbuster left in America. They really want you because they need employees and they need tech employees. So they'll hire you on as, say, the VP of technology at their lone store. But you don't really want to work at Blockbuster because you know it's a failing company. So Blockbuster's engineering team may give you a plus 20 valuation because they'll hire anybody. But you may give Blockbuster a negative 15 valuation because you don't want to work at a dying company. So if Blockbuster hired you, they would receive a net plus 5 value increase to their coalition. Finally, you interview at Spectrum. The Spectrum interviewing team really likes you. You're pretty good. You're towards the top of their list. They don't really need an AI engineer, but you know a little bit of web development as well. And so they really want you for their web development team. So their web development team gives you a plus 12 value score. Now, when you're interviewing with Spectrum, you find out, oh, I will not be working with AI. I'll be working with web development. I really want to work with AI, but Spectrum pays pretty well, and it's an entry-level position, so it's a good way to get my foot in the door. So you give them maybe a plus 8 valuation. So Spectrum would get a net plus 20 value increase for hiring you. So if all three companies offered you a job, you would most likely want to go work at Google because they have the highest net value increase. Finally, with local search, the GMs were randomly selected the same way with both of the round-robin heuristics. Next, we randomly assigned the coalitions. Then we decided potential agents that want to move, and we called those agents movers because they want to move coalitions. And then we found potential moves, where an agent would leave one coalition and join another. And the way that we determined if a move was viable or not was we saw how many agents wanted to move after that move was complete. So let's say I wanted to go work at Google, and me working at Google, I have a couple friends working there as well. So less people want to leave Google once I get there. So that would be a viable move. But let's say I want to go work at Blockbuster, and everyone at Blockbuster doesn't like me. Then more people would want to leave Blockbuster. So that wouldn't be a viable move. So what we do is we find the move, that lowers the overall number of agents wanting to switch coalitions, and we execute that move. We continue executing these moves until either we can no longer lower the number of agents wanting to move, or we hit 0. And if we hit 0, we're Nash stable. So it's great. We really want to get to 0 movers. So the way you can think about this is you start out with a couple of dysfunctional teams. The teams get rearranged, you maybe get a new manager, maybe you get a pay increase, and through all these changes, you come to a stable coalition where you and your worker, or you and your colleagues all enjoy working together, and you want to continue at the same position in the same company. So to test our 3 heuristics, we randomly generated multiple instances of each size, that being 10, 12, 15, and 25 agents. We allowed the heuristics to restart many times to find Nash stable partitions. So for the round robin heuristics, we allowed for about 100,000 restarts, and for local search, we allowed for about 10,000. The reason in the disparity between the number of restarts is that local search is much slower. On the lower size instances, it's about 2 times longer. On the larger instances, it can get up to 3 to 5 times longer. So we ran each instance 10 times for each heuristic. We calculated time taken, number of restarts to find a Nash stable partition if one could be found, and then for local search, we also kept track of the number of agents wanting to move. We took averages for each instance for each heuristic. After our testing, we found that local search was our most accurate heuristic. It took the most time to complete, though. It has more valuation checks because it checks every single agent and every single coalition every single round. We're currently working on ways to make local search faster, as it is the most accurate, and we believe it could be the most useful for larger sized instances. The utilitarian round robin was our second most accurate heuristic. It was faster than local search, but it was also not as accurate. It has less valuation checks, so it goes a little quicker, but more agents slip through the cracks. It is accurate enough and fast enough to be useful on smaller instances, so instances of 15 agents and less. Finally, the selfish round robin was the least accurate of the 3. It had the least valuation checks, so it was the fastest, but a lot of agents got put in incorrect coalitions often enough that the accuracy was severely impacted. We deem it to currently be the least useful of the 3 heuristics. So in summary, utilitarian round robin is currently our most useful heuristic for smaller instance sizes, but we're currently working on ways to improve local search and to devise new heuristics. For ATFGs of size 15 agents and lower, we were able to solve for Nash stable partitions. For agents of 25 or more, we were not able to solve for Nash stable partitions. We believe this could be for one of 2 reasons. Either there were too many restarts required. Based on the 15 instances, or the 15 agent instances, an average of 80 to 90% of available restarts were required to find Nash stable partitions. So for utilitarian round robin and selfish round robin, that was about 80,000 to 90,000 restarts. Our other theory is that as the density, or as the size of the number of agents in an instance increases, the density of Nash stabilizable instances decreases. So as you add more agents, you add more valuations, you add more complexity. So as it becomes more complex, it is harder to find Nash stable partitions. Finally, if anyone has any suggestions on any heuristics we might be able to try, or anything that could be helpful, feel free to reach out to us. Thank you all very much.
Well, thank you. An interesting talk. I've got a question. I'm sure others have questions too, but let me ask first.
Okay.
It looked like the utilitarian method was aimed at finding a manager more than finding members of the coalition. And the others well, the one that you like the best, the local search, didn't even talk, as far as I could see, about the manager. It was talking about building the coalition. Am I wrong about that?
Yeah, so I kind of glossed over the manager selection in the second two, the utilitarian round robin and local search. But for all three algorithms, we determined the manager in the same manner. Agents that wanted to be managers were put in a list and randomly selected. And so for the selfish round robin, the game manager and the coalition's values were all that were taken into account. And in the utilitarian round robin, the game manager and current coalition's values were taken into account, as well as the potential agent's valuation of that coalition. Does that answer your question, Dr. Finkel?
Yes, it does. I've got other questions, but let me open the floor to other people who might want to ask.
Dr. Dromchik sent me a private question. He asked, how do you define accurate and most useful? Dr. Dromchik, is that in regards to finding stable partitions?
Okay, I'm unmuted now. Yes, this, just when you were evaluating your heuristics, you were using that term most accurate.
Yeah.
Least accurate.
Yeah. So when I said most accurate, what I mean is if a Nash stable partition existed, then they had the highest or higher chance of finding them. So if we ran 10 tests on an instance that had a Nash stable partition, then we would define accurate as being finding that Nash stable partition more than not. So 90% of the time or 80% of the time would be considered accurate. And we would consider a heuristic most useful when it can accurately find Nash stable partitions, but when it can also quickly find those Nash stable partitions. So local search finds them at the highest accuracy rate, but it's also much slower than the other two.
So thank you, Christian. If I may ask one additional question.
Yeah, of course.
Testing is a critical part. And using a randomly generated is, in my view, only one type of data that should be used in testing. For example, we should use also something that may come from the domain knowledge, which may be very different from what you are randomly generating.
Okay.
So have you thought about that? Okay.
So we also handcrafted some instances as sort of a baseline where we knew if an instance would have a Nash stabilizable partition or not. So we did craft some just, some easy examples.
So let me also jump in here. We, as Chris mentioned, I think we were unable to find in the randomly generated instances any Nash stable partitions for the 25 agent case. So we looked at cases which were not just random generation. We looked at cases that came out of other hedonic games, like friend-oriented hedonic games, which Chris mentioned earlier. And our algorithms found no stable partitions. So we've looked at, 4 or 5 special cases and still are not getting a lot of love there.
We also looked at asymmetric versus symmetric valuations. So we tested 25 agent instances that were symmetric, that had symmetric valuations, and that had asymmetric valuations. And we did the same thing for the friend and enemy oriented games. So we looked at symmetric friend, asymmetric friend, and symmetric enemy and asymmetric enemy, and did not find any Nash stable partitions as well.
Other questions? Well, let me ask another question then. When you start with, say, 25 agents, are you looking for a set of coalitions with 5 in each coalition, or do you not set any requirement as to how big and how equal the various coalitions should be?
Okay, good question. So depending on the size of the instance, so for example, 25 agents, we allowed an upper and lower coalition size. So for 25, I believe it was anywhere from 3 to 8 agents within a coalition. And then for the smaller instance sizes, so 10, 12, 15, we allowed for 3 to 5 agents within a coalition. And that's including the game manager.
Right, you disallowed, well, you looked to see if someone would prefer to be in a coalition by him or herself, by itself. But that's an invalid coalition because you don't allow coalitions of size 1.
Right.
Now, you're doing hill climbing, it looks like. That is, you're doing a small modification and hoping to get to something a little bit better, which
Correct.
can easily find itself in a local maximum, and which is why you do the restarts, I assume, in order to improve your chances of finding the actual maximum. There are, of course, other methods one can use for trying to, heuristics for optimization. There is simulated annealing, and there are genetic algorithms which come to mind very quickly. Are those worth trying?
Yes, actually, we're currently working on simulated annealing, trying to work on a way to include simulated annealing. We've talked a little bit about genetic algorithms as well. I think our focus right now is making local search a little bit better, working on simulated annealing, and potentially combining algorithms. So maybe you use utilitarian round robin to put out a good partition, and then you feed that partition into local search so that you hopefully start out closer to a universal maxima rather than a local maxima.
Right. Well, just a suggestion, if you want to look more deeply into genetic algorithms, Hank Dietz is an expert at those, and he's used them for many different things.
Okay.
And so he's someone you can turn to. He also has a lot of computing power available. And so if you want to do a lot of simultaneous restarts, he's got the computers.
Okay. Thank you very much.
Do we have any other questions? Well, good. Thanks a lot for the talk. Very interesting. And it's good to see students talking about recent work that you've done. And I encourage people to do that. We have next week already, in fact, for the rest of the semester, we now have an entirely filled schedule, which is very good to see. So if you want to speak, sign up for the next semester. The schedule will be online shortly. So thank you all for coming, and enjoy the rest of your day, and keep current.
Thank you all for your time.